Good evening, everyone. On the behalf of Department of Mathematics, Wilson College Autonomous Mumbai, I welcome you all in the today's session. Our today's guest is Ajay Kumar sir. He is an assistant professor at Department of Mathematics, KR Mangalam University, Gurugram. He will deal with the topic of differential equations today. Over to you, sir.
Yeah, thank you, sir. So, good evening to one and all present here. I hope that all students for the session has arrived. So, today we will deal with a linear differential equation with constant coefficients. So, we will have a introduction. What are its types, like homogeneous and non-homogeneous types? Then we will discuss about its solution structure, like then we have complementary function and particular integral part while solving the linear differential equations. So, so what is the linear differential equation with constant coefficient? So we can see a differential equation of this form: an dny dxn plus an minus 1. So this is, oh, where is the highlight? Yeah. So differential equation of form this type. So here we can see here nth order derivative term, that is dny over dxn, is multiplied by some constant, then some constant multiplied by the less order, that is n minus 1 dxn minus 1. So where all these ai involved here are constants and an should be non-zero. For this differential equation has to be of order n, otherwise we we will reduce our this order for the defining differential equation. So uh, we also write operator method or standard form. So what we do like yeah. So we will put by dx as capital D. Then simply what is d square by dx square is something d square, and like so we write dn over dxn as d to the power n. So we can simply write in this equation in operator form as an, mm, yeah, an d to the power n y plus an minus 1 d to the power n minus y plus a1 dy plus a naught y equals to some function of x. So we can take y common from here. It is nothing but an dn plus an minus 1 dn minus 1 plus a1 d plus a naught y equals to fx. And we simply we can call this as ft. So this is our, we can write here as the operator. So here d is the operator. So d is nothing but a simple derivative d by dx, and similarly d square by dx square is d square, and so on. So we can write this equation in this form: ft phi equals to this small function of x. So here we can define operator as capital Ft. So next we define type of linear differential equation with constant coefficient. So one is homogeneous differential equation and one is non-homogeneous equation. So if right hand side part becomes, that is the small fx is 0 in the past slide as we discussed, then the equation becomes homogeneous differential equation. So in operator form we can write it as f dy equals to 0. And when this fx is non-zero, in the right hand side, we say this as non-homogeneous differential equation. So like this type y double dash plus 2y dash plus x equals to 0, x over 2. So can any student can tell like which type it is? It is homogeneous differential equation or non-homogeneous differential equation?
Homogeneous differential equation.
Sorry, hello. Again, please. I think I
No, sir,
missed your
it's
voice,
a
Anand.
non-homogeneous differential equation.
Yeah, it is non-homogeneous
Homogeneous
because
equation.
yeah. So it is like here x by 2. Okay, this function of x. This term it is there. It is non not equals to 0 here. So it is non-homogeneous differential equation. So and what if we take y dash plus y double dash into y dash plus x y equals to 0. So can anyone tell this will be a linear differential equation? It is linear differential equation or not? It is linear or non-linear? Can anyone tell?
No, sir, it's non-linear because it involves the product y dash.
Yeah. So here it is containing the term y into y dash. So it is a non-linear differential equation. Okay. So next, next we will talk about. I think my screen is auto rotate. Let me do rotate. Where it is. Yeah. Okay. So now we come to the solution part of the linear differential equation with constant coefficient. So we all know this is nth order linear differential equation with constant coefficient. And capital FD is nothing but the operator. So here what is the operator? FD. Like anybody can tell, like one of you have to tell what we have defined earlier. The operators. Okay, so no issues. I already discussed earlier. Yeah, like when we have a differential equation of this time, so how we define the operator here? Operator part, we are just simply writing d by dx as d. Then the higher order terms will simply convert it to d square dn by dx and as dn, d to the power. So when we come to operator, so here fd is what I have defined. Fd is nothing but an. It is nothing an and d to the power n plus an minus into d to the power n minus 1, and just like a1 into d and then a naught. So this is our the operator. This is differential operators. So this is just form, and we will use this in finding the auxiliary solution. So this is an dn plus up to a1 d plus a naught. Okay. So the general solution is complementary function plus particular integral. So first, for complementary functions, what we do, we just solve the from this equation, we solve the homogeneous part. That is the right left hand side, the whole left hand side up to a naught y equals to 0. First we solve this, we then find the complementary function, and if fx is 0, then there is nothing, but there is no particular integral part. If fx is non-zero, then we are dealing with non-homogeneous type. So first step is this, that we have to find complementary function, and then using that operator, this differential operator, 1 upon fd, we have to find particular integral. So here complementary function involve some constants like so here what is the order, and nth order. So we will have constants like c1, c2. So n constants are there, but particular integral part is respective to this function fx. So we there is no constant involved here, and we just simply put this what differential operator. So here we will discuss the cases how we solve this particular integral part when fx is have different type of forms. So we will discuss it first. We will discuss complementary function, and then we will discuss about particular integral solutions. So when we come to auxiliary equation and complementary function. So first, if we have a non-homogeneous equation, that is, I'm simply writing this operator form, f dy equals to fx. Okay. So for auxiliary equation, we are defining auxiliary equation or complementary function part. So we simply put this right hand side part as 0. So this is first step, and second step is particular integral that we will discuss later. So first we look how we solve this part. So I already told this operator. So replacing, now next step is replacing d by m. So we will get a polynomial. So d square will be m square, d cube by is m cube, and so on. Like we have what we say, y is y double dash plus 2y dash plus y equals to 0. It is nothing. What we do, d square plus 2d plus 1 into y. I think there is some issue with my pen. Y equals to 0. So this is easy part, as this is d square by dx square. I already told how to convert it. So simply writing y dash, that is d by dx, as d, and d square by dx square as d square. So this is our equation in what we say operator form. So now we have to find complementary auxiliary equation. So we just replace d by m. So it is nothing but m square plus 2m plus 1, okay, equals to 0, equals to 0. And now uh, we will determine what are the roots of this equation. So here and say easily m plus 1 ka whole square is 0. So it is nothing but m equals to minus 1 2 times. So it is real root, and it is repeating type. So this is a general way. So we will discuss the cases, like case total possibilities are like this. There can be real root and complex root. Then also there is like distinct real roots or repetitive. Same with go with complex, distinct, and repetitive. So next coming, so this is the homogeneous equation. So like anyone of you can try and tell me what are the like what is the auxiliary equation here?
M square minus 5m plus 6.
M square minus 5m plus 6. So what are the roots?
-3 -2.
No, it is
Sorry.
but 2 and 3.
Yeah,
Yeah.
yeah, yeah.
Okay. So m equals to, right? So 2 and 3 are real roots. So what we say this case, this as distinct real roots. So how we write solution for distinct real roots? Like if we have a different roots like m1, m2 up to mn and all are different and real roots. So we just write the complementary function as complementary function can be written as c1 e to the power m1 x plus one root is covered, then next c2 e to the power m2x. Second, and in this type, similarly, we have to cover all the roots value, that is c n e to the power m n x. So this is a complementary function in this case. Okay, and so here the two distinct root are 2 and 3. So what will be the complementary function? Anyone of you can tell me?
C1 e to the power 2x plus C2 e to the power 3x.
Yeah, c2 e to the power 3x. Okay, and this is the solution of this equation, right? Because it is homogeneous, so there is no particular integral value. So next, so yeah, example already I covered. When roots are 2 and 3, we have to write like this. And yeah, when there are repeated real roots, so what we have to do? We have to do simply, if m is repeating twice or let's say thrice, then our complementary function will become c1 e to the power mx. One value is covered. What about next? If we do the same procedure as did in uh, distinct root case, then it will become like this, and it becomes c1 plus c2 e to the power mx again. It is, we can say this as new constant kemx. So here only one root value is considered. So what we do for that? We have to add, we have to multiply the constant. Uh, where it is? Yeah, so we have to multiply. We have to multiply like this: mx plus c2 into x e to power mx, and then next we have to multiply c3 x square e to the power mx. So this part is clear. So whenever we have roots like up to here, it is 3 times. So power will go up to x to the power uh, x to the power 2, like plus whatever the roots are repeating r times. So we have to go up to r minus 1 times, that is c1 e to the power mx plus x times c2 e to the power mx plus x square c3 e mx. So this part is clear to all of you. When we have
Yes, sir.
root and yeah,
Yes, sir.
okay. So when we have root m repeating 2 times, so we just simply write c1 into e to the power 2x plus c2 into x times e to the power 2x. So this repeated real roots case is also discovered, also covered now. Now we go for case 3, complex root. So complex root, so complex root, you all know complex root if I say alpha plus iota beta is the root of some polynomial. Say m square plus whatever it is. Say minus 2m plus something minus 8. So if this having one complex root of this type, then another root will be alpha minus iota beta. So one thing about complex root is it always occurs in pair. So if one root is alpha plus iota beta, then other root is alpha minus iota beta. So complementary function for this type of uh, roots, if we are getting after solving our auxiliary equation, then we write our complementary function as we write the alpha part as we did earlier in exponential power e alpha x. Then the imaginary part root value is covered in cos in trigonometry function, that is c1 cos beta x and c2 sin beta x. So now looking for examples, so we have roots here minus 2 plus minus 3 iota, that is one root is minus 2 plus 3 iota and another root is minus 2 minus 3 iota. So simply we can see this real part is e to the power minus 2x, and then the left part is in c1 cos 3x and c2 sin 3x. Okay, so here is maybe also the case when these roots are repeating two times. So we will this. So here it is a repeated complex root case. So if, for example, we say alpha plus minus iota beta is occurring two times, that is, these are actually four roots, and here alpha plus iota beta, the roots are alpha plus iota beta, alpha minus iota beta, alpha plus iota beta, alpha minus iota beta. So roots are actually repeated two times. So what we do? We will do the same procedure. That is, real root is taking the same value e to the power alpha x, real value, and what about this imaginary value? Imaginary value we have to do c1. So now here you have to do the same as we did earlier in repeated real roots. So this is c1 plus c2 into x cos beta x, and same thing with c3 plus c4 times x sine beta x. So if you don't do this like this, then it will become a new constant. If we do the same thing like e to the power alpha x c1 cos beta x for this one type, and also for second part you do the same thing c3 cos beta x and plus c4 sin beta x. So you do the same thing. C1 plus C3 becomes a new constant. So only you are covering equation, only you are covering to this only one time root. That is k cos beta x, and you say k1 and k2, c2 plus c4 sin beta x. So you are covering only this one value. So for this thing, you have to multiply the constant by x in both the terms. So this becomes the complementary function for the repeated complex roots. So this time it is repeating two times. So we have the power less, that is whatever the roots are. So here roots are repeating r times. So power is going till, it will go till x to the power r minus 1. As here it is two times. So the power is going only one time. So I think this part is clear to all of you. So we can look here as the roots 1 plus minus 2 iota. It is repeating two times. So we will go for the process again same whatever I have told you. So this is 1 plus 2 iota, 1 minus 2 iota, 1 plus 2 iota, 1 minus 2 iota. So we do this e to the power real part value, that is e to the power 1 into x, then c1 here repeating 2 times. So what we do, the next constant is multiplied by x, equals 2x, plus same thing with other next constants, sine 2x. So this is the complement function in this case. So I think for till now we have covered all the roots type and complementary part. Now we will go for particular integral part. So when we look for particular integral, whenever
So I
the
have one question regarding the complementary function.
yes,
So what if the roots are of the form a plus minus b? Then what will be the complementary function in terms of hyperbolic function?
so in hyperbolic function it becomes c1 cos alpha plus minus
Beta?
beta. So it is beta iota, no?
No, it's just beta. The
I
roots are
think
given.
it is root beta, alpha plus minus root beta. You are saying something like that, okay?
Yeah,
Mm,
alpha
maybe, but I have seen
Yeah,
some
yeah.
root.
MCQs.
Otherwise, alpha plus
I
minus
think
beta reduces in the other single real number, okay?
real root. It comes in real root, no?
Yes, it will be root beta,
I
I
think
think.
it is written as e. Yeah, so e alpha x and cos hyperbolic root beta x plus sine hyperbolic root beta x. I think this was the form. As far as I remember, if anyone knows, you can correct. Otherwise, I will look tell you if this is the not the correct way of writing it. It can is in this way, I think. E alpha x cos hyperbolic root beta x and sine hyperbolic root beta x. Is it correct or like I have to?
Mm. Sir, your screen is not visible.
Yes,
Yeah,
That's
yeah, like yeah, there is some this internet issue at my place, I think. Visible? Hello?
yes, now busy.
No visible. So here I have written that form e to the power alpha x cos hyperbolic root beta x plus sine hyperbolic root beta x. Is there any internet issue? Am I audible?
yes, sir, you are audible.
Yeah. So here I have written that form. Or we can is this correct? Anybody like can recall that this is the form in hyperbolic form? Okay.
I think this is correct.
Yeah, this is correct. If this is wrong, then I will like let you know in the coming upcoming sessions. So now next coming to this particular integral part. So when we have a non-homogeneous type of linear differential equation, so we already know how to solve this homogeneous part, that is f dy equals to 0. We look for auxiliary equation, then we find complementary function. Okay, but this right hand side term need a, if this is non-zero, then we have to find particular integral. So particular integral we have to find like this. This is f dy equals to fx. What we have to do? We have to operate this operator fd over fx in this way. So there are a method like when our function fx can be of the form exponential, sin ax, then x to the power n, some x into some function of vx. So we will look over these in next slides. So here it is first case, it is exponential form. So on right hand side, a function over this fx, f dy over fx. This is of the form e to the power x. So what we do, we simply replace d by a. So why we do this? We are just replacing d by a. Can anybody tell? Okay. So why we do like this? That when we take y equals to e to the power ax. So okay. So why we do d of y is nothing but a of e to the power ax. Okay. So we simply replacing d by a here. So I think everybody understand that. Also we can go like this: d square y will nothing but is a square ax. So simply we can replace d by a. So here it should be provided that fa should be non-zero. If fa is zero, then what we do, we use, if fa is zero, what we will do, we just simply write this is ft and fa is zero here. So what we do, we just multiply by x and differentiate the operator that we are having, that is x into f1 upon f dash 2. Still f dash a is 0. Then we will go for further step to find particular integral, and that is nothing but x square upon 2 factorial and differentiating this operator 2 times ax. And simply if still this not works, then we can, f double dash is still 0. We will go for like x cubed by 3 factorial next part and 1 upon f triple d dash d e to the power ax. And so on we can proceed. Okay. It depends like when we should have this part fa should the denominator part as non-zero. Next we have sine and cos form. So on right hand side is of this form sine bx and cos bx. So what we do, we simply replace d squared by minus b squared. So why we do that? The same thing that as we did earlier, like for e to the power ax. So if I take so y equals to sine bx. So if I differentiate it, it becomes b of cos bx. Okay. So here I can't compare like sine bx was my y. In last it was the same thing. So I can't say about anything about d. So if I do again a differentiation with respect to x, it becomes b square and sine bx. So what I have did here, it was y is sine bx. Okay, so I can compare here. So here I can replace d square by minus b square. So I can replace d square by minus b square. So what we do f d sine bx. We just replace f d square only. D square is replaced by minus b square, and rest is left. So it should be provided that the lower part denominator should be non-zero. Same, it works for cos bx. So what we do for cos bx, we do the same thing. dy is minus b sine bx, and then again it is minus b square cos bx. That is d square y. So here again we are replacing d square by minus b square, and we don't replace anything, like we are left with only the denominator party, the polynomial in linear polynomial only of 1 degree. Next one is a polynomial form. So when we have this type of form, f dy equals to x to the power m. So what we do, we just look like this, put f d into x to the power m. So like we say, for example, I say I have taken, okay, I can take expression from here. My operator is 1 plus my operator is 1 plus d y equals to x to the power square. So how do I find the particular integral here? Simply write 1 upon 1 plus d x square. And here these are the binomial series form in operator form. So you all are aware what can be written as 1 plus d to the power n. Yeah, tell me, anyone of you, what is the binomial expression for this? If anybody can tell. Yeah,
So 1
okay.
plus
X. Okay, tell me. Yeah, go on.
is a 1 plus nd
Mm,
plus n
yes.
into n minus 1 by 2 into t square by 2 factorial into t square plus
Mm-hmm.
n into n minus 1 into n minus 2 by 3 factorial into d cube
Yes.
plus dot dot dot.
And, and similarly, dq, and we go up to d to the power n, right?
Yes.
That is again d to the power n. Last term will be this. Okay. So here I directly you can claim these results. These are the simplest ones, like 1 minus d to the power minus 1. So what we it is simply 1 plus d square plus d cube and so on. And next it is 1 plus d to the power minus 1. So here you can replace only this part minus d here in the next thing. Similarly, we have 1 minus d to the power minus 2. So you can directly remember these things or you just remember this part. This will be like easiest one. Like you have not to recall the full binomial expansion of x plus y to the whole power n. So you can directly use this thing. So here what we are getting, it is nothing but 1 plus d to the power minus 1 x square, right? So it is nothing but 1 minus d plus, so it is here, it is the expression, plus d squared minus d cube and so on into x square. So it is nothing, if you multiply it, it becomes x square minus d of x square. That is, what is d? What was d? Our d is one time derivative with us. So it is 2x. What is d square? So it is two time derivative. So it is nothing but 2x. And when we talk about three time derivative of x square, so it is x square to 2x, then it is 2, then next time it becomes 0. So next part is 0. So this whole thing is the particular integral of this non-homogeneous oh, non-homogeneous linear differential equation. Is that clear to everyone up till now?
Yes, sir.
Okay. So next, moving to the fourth case. The fourth case that I already told earlier. So it is something that is e to the power ax into vx. V is some function. It can be anything like eax. Vx can be like, if it is a other function of exponential, then there is no issue. It is converted again into the first case that I already discussed. So now how we do, it has the shifting rule. So what you do, ex into some vx, if you are finding the particular integral part, so just put this out, ex, it is just replace the operator by d2 d plus a into vx. And this is the case that we have already discussed. You have to, what you have to do, you have to replace d by d plus a. So if it is d square plus 2d plus 1 upon and e to the power 2x into x, you have to do this thing. 1 plus, it is 2. So e to the power ax, what is value of a here? 2. So we just replace d to the d plus 2 square plus 2 d plus 2 plus 1, and our e to x is outside, and we are left this operator only. So now we have to deal with this e to x. So it is nothing but d square plus 4d plus 4 plus 2d plus 4 plus 1 into x. So it is nothing but e to the power 2x. It is nothing but d square plus 6d plus 9 into x. So what you can write here, what we have to do next? Can anybody tell how we will deal with this? Anybody can tell. If you have the idea, you can tell. What is the next part? How we will deal with this? Okay, so we can take 9 as out and
So I
1
think it's d plus 3 whole square in the denominator if we add the term.
d plus 3,
Hmm.
d square plus 6d plus 9. Anyway, you are saying you have to replace d by d plus 2 or d plus 3.
Yes, sir.
No, no, it is e to x, e to the power 2x I have taken.
Hmm.
Okay, it was 2 e to the power 2x. Okay,
Yes, sir. That part is okay.
then,
Then here, uh,
hmm,
we are get a d square plus 6d plus 9. So it is d
yeah,
plus 3 whole square.
it is d plus 3 whole square. Okay, d plus 3 whole square. Okay, okay. So now you just simply you can use that part that you have used earlier. So how next you can do e to the power 2x. It is nothing but 3 plus d to the power, or you can put this 3 outside, e to the power 3. So it becomes 1 upon, it comes out to be 9 d plus d by 9 plus 1 to the whole square d by 3. That you have to use that formula again. 1 d by 3 x. So what you can write at e to x by 9, 1 plus d by 3 whole power minus into x. Is it fine? Up to this, is it fine to everyone?
Yes, sir.
Yeah. It is nothing but e to the power 2x by 9. What is the expression for this? It is 1 minus 2d by
By
3. And next term will be plus 4d. What was that? What is the expression for 1 plus d to the power minus 2? It is 1 minus 2d plus 3d
3D.
square. Okay, so it is yeah 2d by 3 and then 3d. So it will become d square. And we know like 2
We
time
don't need
derivative
any
of
more.
this. Yeah, so we will do not need the next term. So it becomes e to the power 2x upon 9, 1 into x minus 2d upon 3, that is 2 upon 3, x differentiation of x. It is 1. Next d square is 2 times derivative of this x. 1 time is 1. Next it becomes 0. So this next rest term will become 0. We do not need that. So this is the particular integral for this equation. Okay. So next, moving case 5. So I think this part, this case is clear to all of you. Anyone can respond like if this part is okay to all of you.
Yes, sir.
Okay, fine. So next we have the case number 5. That is some right hand side part is some function x into some function of x vx. So that is fd. So for this, we have the direct formula. So it can be written as this x into 1 upon ft times v plus derivative of this thing multiplied by v only. So it also can be written as x into 1 upon. So actually this part, what we are doing, we are just uh, converting it into two different terms. So first is this first term, this is second term. So what we do, we just taking x as outside and simply doing the rest, that is using this particular integral part of vx. The next term is nothing but it is f d to the power like the whole square f dash d of vx. So this part, if you solve this, this is the term that we solve from this derivative of this 1 upon fd. It is nothing but minus of 1 upon fd. It is minus of 1 upon fd whole square into fd derivative of this thing. So this is nothing, this term. So I think hope this formula is clear to everyone. And the rest, we do the same procedure. Whatever the terms will come, and we will solve the same as we uh, discussed the cases earlier. 4 cases we have discussed. So we can go through that procedure. So now you can check whether these are the cases this here. So if bx is some function of x to the power n, it is again converting x to the power some m plus 1. So this case is already covered. Next we have x into e to the power ex. This is already we have covered. What we do? We replace d to d plus a. And what we have? ex and 1 upon fd into x. So we are left with only part x into some function of sin x. So here we have to use this formula. So this will be helpful in only these cases. So next, coming to the case of failures. The case of failures when denominator becomes 0, that we have already discussed. When we have Ax, so we replace D by A, and denominators we replace FD to FA, we should be non-zero. If it comes zero, what we do? If it fails once, we simply multiply it into x e to the power ax into, and what do we do? We do the derivative of that our operator ft. We do derivative and replacing again d by a. If again it fails, like what? When it fails, f dash a again becomes zero. So what we do? We again multiply x squared by 2 factorial e to the power ax, and again we do the differentiation of the this term, this operator f dash t. So it is f double dash t. So similarly, now when it fails, we just replace d by a again. Again, when it fails, f double dash becomes zero. So what we go? We go for third third part, that is x cube upon 3 factorial and e to the power ax upon f triple dash t. So again, so simply we can go like r times. If what we have to do, we have to multiply by xr if root is repeated r times. So here it is repeated 3 times. So we have did x multiplied by x cube and we divided by 3 factorial, that is r factorial. You can generate to the, like it is a generalization for if this case happens r times. So now next coming to some questions. So like everyone should try what is the particular integral of this differential equation, given differential equation. So just try at your own. I wait for 1 minute and ask like you can tell me how we can proceed.
Sir, am I audible?
Yeah, yeah.
Sir, I've not understood the particular integral in case of when the particular either cos ax or sin ax, when the f of a is equal to 0. If not equal to 0, then we replace d square by m. If it is equal to
Mhm.
0, then this type in case of cos x and sin x, I have not cleared.
Yeah, you have to do the same thing. If you have sine ax and you have 1 upon ft, right?
Yes, yes. And here f of a is equal to 0.
No, you can't replace d by a, no? You can't replace d by a. I have already told you, if you take y equals to sine ax, then what is dy? Tell me.
It is a cos ax.
Okay, so is it same that you can compare here? It is cos ax. Y is sine
Not.
ax. You can't compare, na? So
Yes,
you
yes.
can't replace d just by a. So in next step, what you do? You just do it differentiating second time. So what it comes? Minus.
A square. That is why we replace if d is minus a
That's why,
square.
yeah. That's why we replace d square by minus a square.
Mm,
Okay.
yes.
And next part you have to solve by whatever the form fd is then reduced. Like you are left with thing this d sum with multiply like some constant value and some constant here, and then you have to solve that part. Okay.
Mm.
So for this question, like anybody had tried? Okay, so okay. So first tell me what is the complementary function here.
Is m square minus m square plus 3m plus 2 is equal to 0.
Yeah. So what it is? What will be the roots?
This is 1 or and 2.
And m minus 1,
minus 2.
m minus 2. Is it correct? It is plus equals to 0. So it is m equals to minus 1 and minus 2. So what is you write the complementary function here? This is auxiliary equation. And here it is complementary function. It should come c1 e to the power minus x plus c2 e to the power minus 2x, right?
Yes, sir.
Yes, sir.
Yeah.
Okay, but we are asked to find out the particular integral only.
Yeah, I have like asked you, can you guys figure out this? What will be the particular integral? Anybody? So what is the operator here? It is d square plus 3d
3D plus
plus 2 and e to the power ex, right?
Yes, sir.
So can you proceed further from this? Anybody? So what we have, we know that if this was some e to the power ax, then we can directly replace t2 t plus a. But it is not the case here.
Yes, sir. We
So
can put it e to the power x is equal to x ln. Sorry. Uh, uh,
no, we can't do that. Okay.
so we can break the operator by using
Yeah,
partial fractions.
yeah. You have to break this operator by using partial fraction. So what it is 3d plus 2. So it is some d plus 1 1 upon d plus 2, right? And what
Minus
constants?
my
Yeah, it is d
yes, there will
plus
be minus.
2 minus d minus 1. Yeah. Okay.
Mm,
Up to this level you reached.
yes, sir.
So next, what you do, you simply do, you can simply write one part is this 1 upon d plus 1 e to the power ex, and another part is 1 upon d plus 2. So you are just simply reduce our this operator form to e to the power ex, right? So it is minus e to the power ex. So now this is first part, this is second part for finding particular integral value. So now how will you proceed?
So we can take the first part equal to v, and then
Yeah,
we can
yeah,
convert
yeah,
it
yeah.
into linear differential equation.
Yeah, that we have discussed in last session. So it is just nothing but 1 plus d of what you can say d plus 1 p1 equals to e to the power ex, and here again taking this as v2, so it is nothing but minus, or you can simply forget this thing minus sign f. You just directly we will use this star expression after solving this part. So this is d plus 2 e to the power ex. So it is nothing but d plus 2 b2. This is e to the power ex. So what is this? This is something like d of v1 by dx plus v1 equals to e to the power ex. Correct? This is what it is. You can find the integrating factor here. Linear differential equation. What is the integrating factor here? You have seen this form, no? Earlier, it was like dy by dx plus px y equals to qx. And integrating factor is e to the power integrating px
it is Euler form.
dx. Yeah, it is Euler form. So it is Euler form.
Yes.
Was it is Euler form? What we call it? It is simple linear differential equation that we did earlier, like when we had done like exact, when we tried to solve this using what is exact differential equation. So here it comes the integrating factor part. So what is integrating factor here? E to the power 1 dx, that is ex. And in this case, here it becomes integrating factor as e2 dx, that is e2x. This part is clear up to this part, what we are doing here. And here the solution for this thing, it is v1 into integrating factor. Integrating factor, and this right hand side part, that is qx e to the power ex dx. This part is clear. And we are finding the particular integral, so we don't involve constant here. So here our v1 is nothing but integrating factor is e to the power x. What do you call, so it is v1 e to the power x, e ki power x, e ki power x dx. So this is nothing, e ki power minus x. And well, solving, what you get, e to the power x. Is this clear? You have to make substitution, e to the power x as t, then ex dx is dt. So it is nothing but integration of t e to the power t dt. So it is nothing. So this reduced to integration e t dt. So integration of this is e to the power t, and what is t? E to the power x. So it is nothing but e to the power x. Till now this is clear. Like what is v1? Similarly we will find v2. So v2 into integrating factor. So I am directly writing here equals to what it is, multiplying integrating factor by right hand side dx. Okay, so what you do, you just simply make substitution e to the power x as t, then it is ex dx equals to dt. So you are left with t e to the power t dt. So you have to do that, use that method for integrating first, second, ILA, TEC. Okay, ILA. So inverse, logarithm, algebraic. So this is algebraic. So first is this. So integrating t et dt, it becomes first, second. So it is t integrating et dt minus what it is, differentiation of first, and then integrate t. It becomes t et minus et. So now replace t by e to the power x. It is e power ex minus e to the power x. This part is clear. So what we are having, v2 into e to the power 2x equals to e to the power x. I can take e to the power ex common here. So ex minus 1 e to the power ex. So in simple, v2 can be written as, it is e to multiply this by e to the power minus 2x. So it is e to the power minus 2x. It is minus x e to the power minus 2x e to the power ex. So v2 is this, and what is v1? v1 is this, v2 is this. So till now, like how we find v1 and how we find v2 is that much clear to you, all of you?
Yes, sir.
Okay.
Sir,
So what we do?
otherwise breaking it into partial fraction, is it not possible to other way?
Like there is no other way, I think.
Because e to the power x.
Yeah, you can do the other way.
So
Other
variation
way is
of
like
parameter we can apply.
yeah, other variation of other approach is that you just put this thing. This is a particular integral, right? So this part should satisfy this equation, whole equation, right?
Yes.
Yes, sir.
So you can directly, this is your y, you just take y dash and y double dash in each of the options, and you can go by this method. So you can make one option as correct.
Yes, sir. Otherwise, a long computation
Yeah.
consume
Otherwise, it is a
time.
long computation. Yeah.
Yes.
So I think so you have to do V1 minus V2, right? So this term got cancelled by this one, and only this term will be left in positive sign, V1 minus V2. Here, this is V1 minus V2 part. So it is, should I write or I can skip? Like, I think you code the concept. Okay, I'll write minus e to the power minus x minus e to the power minus 2x multiplied by e to the power 2x. So first term is getting cleared and it becomes e to the power minus 2x e to the power ex. It is e to the power ex. So it is, correct option is B. Okay, you can do that method. Okay, you could just for each option you have to check what is your, this is your y, and you just simply take y. Or yeah, you can look a pattern here, all of you. E to the power ex, e to the power ex, e to the power ex, e to the power ex is in each of the terms, right?
Yes, sir.
Yes, sir.
So what you do, you just e to the power ex is common. So you are just taking y as e to the power ex. And what is next? That is, you are just multiplying by e to the power some alpha x. 8 minus x minus 2x, and 1x, right? And you can simply find
Yes,
the
sir.
value of alpha here. So what is y dash here? E to the power ex. If you do the differentiation of this, what is y dash? Tell me.
Alpha e to the power alpha x.
Hmm.
Alpha.
E to the power x, right? Plus alpha e to the power alpha x e to the power ex. Correct?
Yes.
And what is y dash? Oh, sorry, y double dash. So first, what you can take common, like you can write here y dash, you can take common e to the power ex, e to the power x, e power alpha x. Then also you can take e to the power alpha x as common thing. Next, you have ex plus alpha, right?
Yes, sir.
So wait. So now what is y double dash?
Sir, it is again y e to the power x, y dash is equal to y into e to the power x plus alpha.
Again, like should I do or
Uh,
what
we
it is?
can we can find out is it?
Yeah, you can just simply put
Yeah,
like you
yeah.
have to, okay. So you have to do first time this and remaining term as like I can do as well. I think the time is up. I can do one more question. So you can go by that approach and you just equate this. Whatever with the left out, you just equate and find the coefficient value of alpha. Okay.
Yes, sir.
Yeah. So now everyone should try this and tell me the answer for this question. Full solution. What will be the full solution?
Sir, what I here we have to find particular integral or as a whole solution.
Full solution.
Okay.
What it is, complete complementary function plus particular integral. So, any other student from today's session? can reply me how we will go in solving this question? Like there is like no other students are there who want to try.
The complementary function is C1 plus C2x e to the power 3x.
C1 plus C2 e to the power 3x.
C2x. There are repeated
Okay,
roots.
okay. So here I think you made m square minus 6m plus 9 as your auxiliary equation, and you have
M minus 3
take
whole
the
square equal to 0.
yeah, m equals to 3 and 3 two times, right? So this is the complementary function. What about particular integral? You can tell if you have solved. You have to write the operator form for this part. So it is d square minus 6d plus 9, right?
So here the denominator is 0 on substituting d equal to 3.
So d
So we
equals
have
to
to
3, you are getting f of a as yani f of 3 is 0. So
so
what
we
you
have
do?
to
You have to
differentiate
multiply
x
it by
multiply
x
and
and multiply the this
opera
part.
differentiate the operator.
Differentiate, yeah. 2d minus 6.
6
Again, it is 0.
again 0. So again
So
we have
what you
to
do? And differentiate this thing, right?
mm,
So this is nothing but x square upon 4
e to the
e
power
to the power 3x. So what is the complete solution here? C1 plus C2x e to the power 3x plus x square upon 4 e to the power 3x. So this part is clear to everyone.
Sir, my particular integral is coming out x square by 2 factorial into e to the power 3x. Extra half.
Extra half I have already told, no? If you are
Yes.
doing r times differentiation, then you have to divide like you have to put in denominator you have to put r factorial as well.
Yes. Here we are differentiating two times because factor is repeated two times. That is why
Yeah,
factorial is
yeah,
coming here. Another
yeah.
half. Otherwise, it would if it were a minus 3 raised to the power 3, then
Hmm.
here we can write as instead of 2, 3 extra.
Yeah, 3 factorial. It, 3 factorial will come extra. If this part is also comes to 0, no, then if we go for second, it will come like x3 upon 3 factorial and some e power 3x and some what is derivative term part here. Okay,
What is the left after derivative?
what is the left after derivative? Like here it is not like that.
Okay.
Here you are just only left with 2, so you can't proceed further, right? So it
o-
will, so some at some point the denominator term becomes non-zero
Okay, sir. And
when you
that
replace.
non-zero factor is extra sitting here.
Yeah, that this is the factor. Okay,
Okay, okay.
okay. So
mm,
coming to next question. So you can take screenshot for this question and you can try.
Okay, sir. I'm trying as a full solution.
Okay. Yeah, for full solution and for also
can
this
you
you can
send the
also try.
PDF?
PDF. Okay, I'll share the PDF.
Sir, have you shared the previous day or whatever you have done on
Like, yeah,
yes.
for both sessions, I will share the PDF.
Oh, okay, sir. Thank you.
Okay. For also, you can try this at your own. This is simplest way. Like I think I have already covered.
Yes.
Okay.
Hmm.
Okay. Okay. You can take screenshot. Hello, sir.
Yes, sir.
Yes, sir. So I think I
Participants,
have
if you
already.
have any further queries, then now you may ask to sir one by one. If you have any further queries, go for it.
I think they have already asked me, sir.
Yes, sir. I
Okay.
hope there are no more queries left. Thank you so much for such an engaging and wonderful session, Ajay sir.
Okay, sir.
Thank you, sir.
Participants, please note that next session will be on Friday, that is 16 January 2026, from 6 p.m. to 7 p.m. as per the schedule. Let us meet there. Goodbye.